Hi folks, welcome back to Physics with Captain Rod. Making this one here to help you out with number 37, no, 27, 27 in your engineering mechanics homework. So the first thing you do with these internal loading problems usually is to find the reactions. So first thing you do is a free body over here of this entire structure. Let's see. Now, we're going to have an AXAY, no doubt about it. We're going to have a CXCY. Now, this load distribution, I would just break it into a triangle rectangle. If we break it like this, the rectangle here is 6 by... oh, whoops, I'm sorry, I got a barking dog here. That's going to take some work, I guess, isn't it? All right. You're going to need this load function here. This thing's linear, so it's going to look like an AX plus B. It goes through the point 0, 200, and it goes through the point 6, 400. Find the slope and the intercept. And actually, the intercept you can read right off the graph here. That's 200. So once you find this function here, then what you can do is... Oh, to tell you the truth? Okay. That's probably not even needed, to tell you the truth. Let me back up here. Let's see. Breaking this like so, that is 200 Newton per meter. That means this distance is also 200 Newton per meter. So yeah, this would have been fine, but I guess we don't need to do that. So our rectangle here, right, is going to have a magnitude of 200 times 6, and that goes at the centroid of the rectangle. So that's going to be like here. I'm just going to put like F1 here. That's for you folks. Or I'll put an F sub R, force from the rectangle. Okay, the triangle now, keep in mind that this is 200, this is 6. So you're going to have a 1/2 200 times 6. I'm going to call that F sub T for the triangle, and that's going to go 1/3 from the corner. So you're going to have another force over here from the triangle, and again, these distances would be known. All right, so we look at a free body now. First thing I always do when I look at a free body is count the unknowns, and I go 1, 2, 3, 4, and I go, ruh-roh, Shaggy, that's no good, because we can only write 2 force and 1 moment equation for this free body. So let's go back and inspect the original structure here, and notice that CB is a 2-force member. There's no loading on it other than at B and C. So with 2 force members, what that means is that the forces have to, how do I want to put this? When you have any sort of 2 member, it only has 2 forces. Not only do they have to be equal, but they have to be what's called collinear. They have to be in opposite directions because, and they have to go, basically they have to pass through one another, because if they didn't, look what would happen. So if I had if I had 2 forces equal in magnitude, but they had some sort of offset, you would have a net couple moment, which is not the case here if this thing's in equilibrium. So what we're going to do is use the fact that this thing is a 2-force member to go back to our free body, and C is really at a known direction, to tell you the truth. That force on C has to be kind of up and right, and it has to point right through D. So here's an angle theta, and you can calculate that angle. It's that angle right there, 2.56. So now the number of unknowns, remember that's a known theta, is only 3. We don't know C, we don't know AX, we don't know AY. Write a moment equation about A, that's going to get you C. The moment produced by C, you'll probably want to write it in 2 forms. Like you'll have a CX times this distance, and a CY goes right through that point, so I guess you can ignore that. And then you'll have this times this distance, this guy times this distance. Again, these are known force values. So that will nail down C. Once you nail down C, do a force equation X direction to get this, force equation Y direction to get this. Okay, now to get the internal loadings at D. There's a couple ways to do that, and think what my preference would be if I were working this thing, I would take it and we'll just cut the system right there at D. All right. Get rid of some of the stuff we don't need. All right, we'll deal with this in a minute. All right, so put your reactions at A that we have found earlier. And really, this is gone as well. So you're going to have an AX and an AY. Sorry about the crummy writing. I'm sitting on my couch. Okay, at the end point here, standard internal loadings in their standard direction, a shear, a moment, and a normal. All right, now we got to deal with this. This was the part about finding this function, by the way. So I'm going to back up. I would probably find this load function. All right, it's linear. The slope is pretty easy to find, 400 minus 200 over this distance, right? So that's what that value is. The intercept you can read off the graph. Here's the part we're going to need that. You're going to need this height right here. Based on the geometry, I'm pretty sure it's 300, but if you ran a 3 through this function, that's what's going to come out of that. Then you can break this load down into two different pieces. A rectangle. All right, there's going to be a force vector down for that. I'm going to call this F sub r for the rectangle. It's going to be 1.5 meters from the left. Magnitude equal to this area, 3 times 200. And then a triangle. Let's change colors here. So then you've got this triangular load. You're going to have a force vector for that. Equal to 1/2 base times height at a distance of 1/3 from the corner. Now, these would then be known values. Moment equation about A will get you, whoops, no it won't, because you'd have shear and moment. Force equation, Y direction, will get you this shear force. Then write a moment equation about A to get the bending moment here. And then force equation x direction will get you the normal, and there's all 3 loadings here at that point. So that'll get you through that problem. Make sure you enjoy these. They're cool. Have a great day.